We're going to look briefly at a couple of aspects of the gravitational force. I think in a previous video in the kinematics unit we discussed free fall and terminal velocity, and we're just going to look at that again from a forces perspective. So just a reminder, free fall is when an object is falling without air resistance, and technically this is not possible except in a vacuum, but we can kind of consider it in general situations where we say there's no air resistance. So it'd have to be a very aerodynamic object, really small, like maybe a penny falling. We could say that that was in free fall. Technically not, but we can use it to idealize a situation. And terminal velocity is the maximum speed an object can fall. And we use v sub t to represent it. And of course that's going to depend on the object's shape because it depends on the air resistance experienced by the object. So for instance, if I have an object and it's falling, so let's say we drop it from a plane from a really kind of high distance, it's going to have a gravitational force on it that depends on the mass of the object that was dropped, and it is going to have an air resistance as well. So there's going to be a resistance force on that. And this is a really low speed, okay, so it's going down already, but it's got a really low speed on it at this point. The thing is, the faster it goes, the more air resistance takes play. So as our speed increases, our gravitational force remains about the same, but the resistance force increases. Eventually, it gets to a point where the speed is high enough that these forces are equal. And when this happens, we know that if net force is 0, then acceleration is 0. So that means the velocity is no longer changing, and this is when we have hit the terminal velocity. If you now have this object, open up a parachute or something and create more air resistance, then the object would actually slow down because air resistance would be greater than gravity. But in any case, I just wanted to give you a quick idea of how terminal velocity can be reached. Quick look at gravitational fields. First, a definition of force field. It is an area around an object within which a force can act. So I want you to take the force field definition you have in your mind from sci-fi type movies, and remember that we can't actually create a force field, right? We can't stop someone from penetrating an area. A force field is just an area around an object where the force acts. So for instance, let's say this here is Earth. Okay, so this is Earth. So the area around it in which gravity can pull in would be part of its gravitational field. Now technically, a gravitational field is infinite. There would obviously come a point where it would be so small that we don't feel it as much. So for the purposes, we say it has a gravitational field, but technically that field is infinite. We can feel the gravity from all the planets and the suns and the stars, etc. in the whole universe. They're just so far away that the difference they're making is really small. And that field strength itself, well, think about our equation we've been using for the force of gravity. Mass times acceleration due to gravity. So we can rearrange this if we divide both sides by mass. The gravitational field strength is the force of gravity something puts on an object divided by the mass of that object. So we can actually find the gravitational field strength for any given object in any given area on any given planet, etc. And this is something that's not in your textbook, but is something that can be important. This is the gravitational equation when you're talking about two large bodies, so mass 1 and mass 2. So it would be like if you wanted to know the gravitational field strength between, say, Earth and the moon. Well, you can make m1 the Earth and m2 the moon, and r is the distance between, and g is a given constant. Can't remember the value at this moment, but capital G is a constant, and we can get the force of gravity between two large bodies with this equation.